Hello everyone, my name is Mikhail Balanic and I'm a research associate at Fraunhofer HHI Institute in Berlin, Germany. Today I would like to present our latest developments and proof of concept summarized in a live demonstration of an autonomous link capacity adjustment in optical metro-aggregation networks as part of the Optical Fiber Communication Conference 2024. I'd also like to thank my colleagues from HHI listed in the co-authors, as well as acknowledge that this work was partly funded by the German Federal Ministry of Education and Research, BMBF, in the framework of the flagship project 6G RIC, as well as Green ICT. So in current traditional optical networks, the link capacity is set statically over the entire lifetime of the optical link. However, with the commercial availability and continuous development of tunable, flexible, and programmable optical components, the statically configured optical networks are slowly evolving into dynamic, reconfigurable, and programmable infrastructures, where the link capacity will be allocated dynamically on demand. So the natural question comes, why do networks need dynamic link capacity allocation or adjustment? Well, this offers a list of different advantages, such as a higher flexibility in provisioning of network resources, meaning capacity is allocated on demand, reduction of operational expenditure costs like energy consumption without actually decreasing the quality of service, and then improved operation efficiency on network operator side, since it allows for a better utilization of available resources and network infrastructure. Therefore, in terms of motivation behind this work, our scope was to develop an efficient machine learning assisted network automation solution for autonomous and dynamic link capacity provisioning based on traffic forecasting, that is, allocating additional link capacity resources when the ingress traffic is expected or predicted to increase, and switch link capacity resources off when the traffic is forecasted to be low. In this work, we present the concept of autonomous dynamic link capacity adjustment deployed live on a real optical testbed at Fraunhofer HHI premises, comprising commercial or experimental hardware, as well as open source and self-developed software tools. The developed link capacity adjustment control loop that you can see on the right-hand side comprises the following building blocks and the tools. A customizable telemetry agent for traffic monitoring, the blue circle, deploying second granularity telemetry streaming related to the traffic rate statistics, an online traffic forecasting module, the green circle, employing the latest machine learning model, the so-called temporal fusion transformer, or TFT, for time series prediction. Thirdly, dynamic capacity allocation module, the red circle, that computes the new scheduled capacity values based on the forecasted traffic load. And last but not least, a netconf native network reconfiguration module, the gray circle, that reconfigures the optical transponders according to the newly computed scheduled capacity values. Finally, we showcase the first prototype of the capacity adjustment control loop in real time and visualize its operation using specially customized Grafana dashboards. When it comes to its deployment, the link capacity adjustment control loop that you can see in this figure is implemented on a hardware and software layer of components. The hardware layer consists of an optical network testbed at Fraunhofer HHI premises, comprising a high-performance programmable traffic generator or optical network tester from Viavi, which generates traffic streams using real traffic profiles collected also at HHI over a period of 17 weeks. The traffic generator feeds the aggregated traffic into an aggregation switch from Mellanox, where these two components emulate the aggregated traffic from multiple optical access networks. The traffic is then routed to an optical metro-aggregation network comprising 3 ROIDM and transponder nodes from ATRAN, interconnected in a ring architecture. The Optical transponders are netconf native and reconfigurable, allowing for their optical line ports to be configured for either 100G or 200G using QPSK and 16-QAM modulation formats, respectively. The software layer of the control loop is deployed on a virtual machine within the Fraunhofer Edge Cloud, FEC, in which each component is operating in a dedicated Docker container, while the entire system is orchestrated using Docker Compose. I will talk about each software component in more detail in the following. Now, when it comes to the system operation, the interaction between the software and hardware components can be seen in this workflow diagram. The earlier mentioned developed telemetry agent queries the telemetry data related to the aggregated traffic at the aggregation switch level with a 3-second granularity tact, collects 20 telemetry samples and computes the traffic envelope, that is the maximum traffic rate for each minute, writing both the telemetry data and the computed envelope to the time series database InfluxDB, which acts as a data lake. Next, the developed machine learning-based traffic forecaster, employing the temporal fusion transformer, performs traffic predictions 5 minutes ahead and writes the predicted traffic envelope values back into the data lake for storage. As the next step, the dynamic capacity allocator queries the predicted traffic values from the data lake, and based on these values, calculates the next scheduled capacities, which are then pushed to the network element or transponder reconfiguration module. The reconfigurator itself compares the current transponder's line port rate or capacity to the scheduled ones and performs the transponder reconfiguration beforehand when required to meet the new capacity demands using a netconf request. Worth noting is that the transponder typically requires around 150 seconds to be reconfigured, which is an interval during which viable and efficient optical protection lines have to be in place to reroute the traffic at the aggregation switch level, while the optical transponder is being reconfigured. This was out of the scope of this work, however, and will not be addressed, but is an important aspect to consider in production deployments. Finally, before presenting the demonstration itself, here is a short overview of the telemetry framework and machine learning pipeline architecture, both at the hardware and software levels, and how these components interact with each other. Worth noting is that only InfluxDB and Grafana are open source solutions that have been used in this demo. The rest of the components or modules have been developed using Python and popular Python packages. So the first component is the CLI-based telemetry agent, which, as I mentioned previously, queries the traffic-related telemetry data from the aggregation switch with a 3-second time granularity and computes the traffic envelope or traffic maximum rate each minute. Then we have the InfluxDB, the open source time series database, acting as the central data lake for storage of telemetry events, traffic forecasts, and newly computed capacity values. And we also have the machine learning-based traffic forecaster, which performs multi-horizon forecasting of future traffic maxima or traffic envelope 5 minutes ahead, based on the previous and current maxima values collected during the previous 30 minutes, and using the TFT model. Next is the dynamic capacity allocator, which computes the expected capacity values based on the mathematical relation given here, where R tilde of Ti plus n are the n predicted maximum traffic rates, or 5 values overall, 1 per minute, and delta C is the capacity adjustment step of the optical transponder, equal to 100G. The network element reconfigurator represents a netconf client used to reconfigure the transponders according to the newly computed capacities. Then we have the transponder monitoring module representing a netconf-based monitoring client used to retrieve different optical operation parameters such as optical received and transmitted power, bit error rate, signal to noise ratio, and so on. Its operation will also be presented in the live demonstration. And finally, the Grafana used for framework and the pipeline operation visualization. This brings me to the end of my presentation. Thank you very much for your attention. And now, without further ado, I will switch to the live demonstration of autonomous link capacity adjustment. Now, when it comes to the live demonstration, the operation of the link capacity adjustment control loop is presented through these two Grafana dashboards, the one on the left-hand side and the one on the right-hand side. I'll go through each separate dashboard and will explain the telemetry framework and machine learning pipeline operation in more detail. So on the left-hand side, three different smaller dashboards are presented. The first upper dashboard shows the current live real-time traffic samples, the green curve, reported through telemetry by the aggregation switch with a 3-second granularity, as well as a traffic envelope, the orange curve, computed by the telemetry agent. The traffic envelope was used to train the traffic forecaster, which was then deployed to predict the future traffic maxima or traffic envelope evolution over time, 5 minutes ahead into the future, the blue curve. Please note that the green curve represents the real traffic profiles previously collected and now deployed for a real-life use case scenario. In this case, for demonstration purposes, 1 minute of traffic translates into 1 hour worth of real traffic, meaning that 24 minutes of these traffic profiles represent 1 day or 24 hours of real traffic. The traffic emulates the daily tidal effect of traffic evolution, where during the early day hours and late night hours, the traffic flow intensity is low, but increases gradually, reaching its peak during the noon and afternoon hours. Next, in the second middle dashboard, the future schedule capacity values are displayed by the blue curve, which are computed based on the forecasted traffic envelope above, also represented by the blue curve, using the earlier shown formula. The red curve, on the other hand, represents the current transponder's network link capacity or optical line rate value, which, as you can see, follows the schedule capacity provisioning curve. Notice that in some cases, such as in the traffic profile at around 1837 or 1903 approximately, a delay between the scheduled and the actual link capacity can take place due to the reconfiguration delay of the optical transponder, which results in this reconfiguration lag, which, as I mentioned previously, can reach up to 150 seconds. Finally, we also compute the value of over-provisioning, the blue bars, which represent the difference between the current link capacity and the maximum traffic rate or traffic envelope. Also, very important, if we look at this second dashboard, we can see that at this very moment, the transponder was reconfigured from 100G to 200G, which is basically the moment when the reconfiguration module presented earlier sends a netconf request for the optical line rate reconfiguration from like 100G to 200G. Last but not least, in the third bottom dashboard, we compare the dynamic capacity allocation scheme with the traditional static capacity provisioning, in which the link rate is set to be constant at 200G during the entire operation time. And we additionally compare the amounts of over-provisioning of these two schemes, the red bars versus the blue bars. Next, on the right-hand side, we present a real-time monitoring of the optical transponder module, where the different optical parameters, such as the optical received and transmitted power, signal-to-noise ratio, and bit error rate, are monitored in real time. Notice that the values of the optical received and transmitted power, minus 10 dBm or 0 dBm respectively, and SNR, approximately 17 dB, remain always almost constant, with short interruptions when the transponders are actually reconfigured. These represent the periods during which the monitoring is interrupted due to the transponder's light path being turned off temporarily during reconfiguration. Also,
Interestingly enough, if we compare the delays at 1840 and 1905, it becomes clear that the second delay is twice as long as the first one, which coincides with the delay duration seen on the capacity allocation dashboard, second left-hand side. It is worth noting that, to the best of our knowledge, current commercial optical transceivers, or transponders for that matter, do not offer on-the-fly reconfiguration without tearing down the optical service. As mentioned in my presentation earlier, one potential solution for this short disruption or disadvantage is to temporarily employ or activate a protection path, which has not been in the scope of our work so far. Finally, when monitoring the BER, the bit error rate, we can see that its values are actually varying substantially between 10 to the power -9, -10 bit errors per second in the case of optical line ports being configured at 100G, and 10 to the -3 bit errors per second when the line port is configured at 200G. This is due to the fact that at lower port rates, the deployed modulation format is QPSK, which offers a more robust constellation against the bit errors and channel noise, as opposed to 16 QAM at 200G, which has a higher bit error susceptibility. This brings me to the end of my presentation and of our live demonstration. I would like to thank you very much for your attention. And if you have any questions or comments related to our work, please feel free to contact me or any of my colleagues at Fraunhofer HHI. Apart from that, I wish everyone a successful conference.